Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we'll be discussing Module 10, in which we apply constant rates to the topic of measurement. You see, measurements usually involve constant rates because we talk about such things as there's always 16 ounces to a pound, always 12 inches to a foot. But sometimes the measurements involve us with terminology that we're not used to, and that can sometimes be frightening. I'm reminded of the story of the man who on his 30th wedding anniversary decided to get something nice for his wife. He went into a pet store. He found this beautiful bird that spoke 14 languages. He decided to get that for his wife. He had it sent home. When he came home that evening, there was this beautiful bird all prepared for supper. And the fellow said, "Gee, how come chicken tonight?" And she says, "I don't know, somebody sent a bird over to the house." He says, "You cooked that bird?" That bird spoke 14 languages. She says, "So how come it didn't say anything when I started to kill it?" Basically, language can be a very tough thing. And in our case, we want to do just the opposite. We don't want to be psyched out by language. And I want to show you today how you can handle things like the metric system, or for that matter, any kind of measurements that you may never have heard of, just by understanding the dimensional analysis that we talked about last time. So without wasting any further time, let's go over to the board and look at a couple of situations. The first thing, as I say, don't be psyched out by language. Let me give you a problem that's certainly beneath your dignity to do right now, but there's a point I want to make here. The first problem says, if there are 2 nickels per dime, how many nickels are there in 3 dimes? And I'm sure that you have the answer as being 6 nickels before I even finish the problem. And there are probably lots of ways you could have done this, but in terms of reviewing what we've done so far in this course, one way of doing this is to observe if there are 2 nickels per 1 dime. Remember what we said a long time ago? In any rate problem, as long as you multiply both numbers in the rate by the same amount, you don't change the rate. So to go from 1 dime to 3 dimes, you multiply by 3. But if you multiply by 3 on one side, you have to multiply by 3 on the other side. So you wind up with what? 6 nickels per 3 dimes. And if you want to do this by our dimensional analysis, you're given dimes, you want to wind up with nickels. To get rid of the dimes, since they're in the numerator, you put them into the denominator. And since you want to talk in terms of nickels, you put nickels in the numerator. Then since there are 2 nickels per dime, you put the 2 next to the nickels, the 1 next to the dime. You check very quickly by canceling the like denominations. Make sure the remaining noun is the one that you want. Then you just do the resulting arithmetic. 3 times 2 is 6. 1 times 1 is 1. So the answer would be 6 over 1, which is 6 nickels. At which time you say, well, that's an awful hard way to do an easy problem. Well, here's what I'm leading up to. Let's suppose I now invent my own language. And for the time being, I'm going to let you in on that language. See, the word nickel is going to be replaced by the word koog. And if you don't know what that word means, don't worry about it. I don't either. I'm just making it up. And now the word dime will replace by moog. So every place I see the word nickel, I put in the word koog. Every place I see the word dime, I put in the word moog. Technically speaking, should changing the name of the object change the concept? Excuse me for a second. Okay? Now, let's reword that problem, or rewrite it, worded the way it is over here. Problem now says what? If there are 2 koogs per moog, how many koogs are there in 3 moogs? Oh my God, this sounds like a tongue twister. And if you tend to panic over nouns that you haven't heard before, this is good grounds for panic. But notice that the philosophy of this problem hasn't changed. One way of doing this is I know that there are 2 koogs per 1 moog. Since I want koogs per moog, to get from 1 moog to 3 moogs, I have to multiply by 3. If I multiply a rate by 3 on one side, I multiply the rate by 3 on the other side. I wind up with what? 6 koogs per moog. But the psychological problem is, if you're afraid of the language, the chances are you can't think in it. And that's why I'd like you to get used to the idea of dimensional analysis. You see, just read the problem. It says, how many koogs are there in 3 moogs? In other words, the 3 moogs are given. You want to find koogs, so you want to go from moogs to koogs. Since moogs are in the numerator, I hope a dean doesn't walk by or something hearing me talk like this. Moogs are in the numerator. We put moogs in the denominator. That puts koogs into the numerator. Now, how many moogs are there per koog, or vice versa? We're told there are 2 koogs per 1 moog. We don't have to know what a coug is or what a moog is. We know there are 2 cougs per moog. We cancel out the common denomination. We have the right label. We do the resulting arithmetic, and we get 6 cougs for the answer, even if we don't know what a coug is. Now you say, well, who cares? Something that dumb. Well, let's pick some measurements that are well known, but maybe ones that you're not used to measuring in. Problem number 3 says, if there are 110 fathoms per furlong, how many fathoms are there in 3 furlongs? And you may say, well, how am I supposed to do this problem? I don't know what a fathom is, and I don't know what a furlong is. You don't have to. You see, it's a rate problem. We know that there are 110 fathoms per 1 furlong, and we want to know how many fathoms there are in 3 furlongs. And by the way, that's the same philosophy as the 2 problems we just did. You see, you know how many fathoms there are in 1 furlong, so in 3 furlongs, there are going to be 3 times that many. So we multiply by 3 on both sides, and we get what? 110 times 3 is 330. 1 times 3 is 3. So there are 330 fathoms per furlong. And if you were afraid of that language, again, go back to dimensional analysis. The given is the 3 furlongs. See, 3 furlongs is how many fathoms? So what do? We want to get rid of the furlongs. So we put those into the denominator. We bring in the fathoms. What's the relationship between furlongs and fathoms? There's 110 fathoms per 1 furlong. And how do we know that? We're told that. We're told that. And once we know that, we simply do what? Cancel the like terms to make sure you've got the right dimension, then just do the resulting arithmetic. By the way, for those of you who are interested, we do have logical derivations for the words fathom and furlong. Fathom is 6 feet, and it was used aboard ship in ancient times as a measurement, and a furlong is 1/8 of a mile. So if you hear about a horse race that's 7 furlongs, that means it's 7/8 of a mile. A fathom is 6 feet, and by the way, that's how Mark Twain got his name from Samuel Clemens, when he was a riverboat pilot. One of the ways before they had radar that they would test to see how deep the water was is they would have a long rope with a lead weight at the end of it, and they had colored ribbons at every fathom, every 6 feet. And the person called the leadsman would wind up like a cowboy and just throw this lead line. It would fall into the water, and when the ship pulled alongside, they would read what marking it was. And frequently, to indicate that you were in 2 fathoms of water, they would yell by the mark 2. See the second mark? And a very common word for 2 was twain. And so he would hear this phrase, by the mark twain, and that's how he got his name, which has absolutely nothing to do with the metric system or with measurement, but I just thought you'd find this to be a nice story. In fact, if this series was 5 programs longer, I could tell you everything I knew. Anyway, let's go on with this and watch how this works again. You see, the next problem says, how many furlongs are there in 770 fathoms? You see, one of the problems that happens now is, you know that there are 110 fathoms per furlong, okay? What's tricky is, you know you're either going to multiply or divide. You sometimes don't know which. And all I wanted to show you was, you can do these problems in other ways, but if you use dimensional analysis, you'll never have to worry about that. Because you see, this problem says what? I'm going from fathoms to furlongs. That means I want to divide by fathoms, multiply by furlongs. You see what's going to happen over here? See, the fathoms cancel. Now I do the resulting arithmetic. My numerator is 770, my denominator is 110, and remember, whatever's in the denominator, that's what you divide by. You see, the 110 took care of itself to be in the denominator because it follows the fathoms. You see, there's always 110 fathoms per furlong, whether fathoms is in the numerator or whether fathoms is in the denominator. So basically, you see, the answer to this problem is just going to be what? 770 divided by 110, which is 7. Now, the reason I'm leading up to this is that one of the things that we often have to deal with in today's technology is something called the metric system, which I won't pass judgment on as to whether it's important to know it or not to know it. We may make a few comments as we go along, but for the time being, let me just show you how you don't have to know the metric system to answer certain questions in the metric system. Problem number 5 says, if there are 2.54 centimeters, which is abbreviated cm, per inch, how many centimeters are there in 10 inches? You may remember this as one of our illustrative problems from the preface lecture. You see, people see the word centimeters per inch and they get uptight. But now that we know how to handle dimensional analysis, how do we read this problem? We say, well, let's see, we want to convert 10 inches into centimeters. We want to go from 10 inches into centimeters. So since inches are in the numerator, we put inches in the denominator. Then we put centimeters into the numerator. What's the given relationship? The 2.54 modifies centimeters. The 1 modifies inches. So now the dimensions are correct. These cancel out. And now we do the resulting arithmetic, and we have what? 10 times 2.54 in the numerator. That's 25.4. The denominator is 1 times 1, which is 1, so we leave that out. And the answer is 25.4. There are 25.4 centimeters in 10 inches. And by the way, if you're not afraid of these dimensions, if you're not afraid of these nouns, you get that answer very easily. You say, look, if every inch has 2.54 centimeters, 10 inches are going to have 2.54 centimeters 10 times. But what I'm trying to show you is we can even overcome your fear if you learn to master little things like dimensional analysis. Of course, what's so important about 10 inches? We don't usually measure things in 10-inch lots. Usually in our English system, we use measurements of a foot, an inch, a foot. Let's just change this problem slightly. Problem number 6 says, how many centimeters are there in 1 foot? And the trick to remember here is that 1 foot is 12 inches. The word foot has an interesting origin. You see, the English people who made up this system were quite earthy. And the word foot is actually what it suggests. To get a unit of length that was uniform, they actually took the length of the foot of a particular king of England. And that by decree became known as a foot. Then they divided the foot into 12 equal parts, because remember, this was before the decimal system, before place value. 12 was a better number for arithmetic than 10. Remember our 12 versus 10 discussion we had when we were talking about place value and fractions a while back? You see, so basically, the English used a system of 1 foot. They measured horses in hands. They actually picked something called a hand. They measured weights in stones. It was a very, very graphic type of measurement system. But at any rate, there were 12 inches to a foot. So basically, now the problem says, how many centimeters are there in 1 foot? So the point is, here's how we use the dimensional analysis now. We want to get rid of feet. But if we knew the relationship between feet and centimeters, we wouldn't be doing this problem in the first place. What we do know, however, is a relationship between feet and inches. And there are what? 12 inches per 1 foot. See, if I look at what I've got done so far, forget the rest. If I look at what I've got done so far, the feet have canceled. What's my answer so far? 12 what? 12 inches. You see, so far what I've shown is that 1 foot is 12 inches. There's nothing wrong with that. The problem is I wanted to know how many centimeters there were. So now I want to get rid of inches and bring in centimeters. See, so I put inches in the denominator, and now I can put centimeters in the numerator because I know the relationship between inches and centimeters. What is the relationship? 2.54 centimeters is 1 inch. So now I check by canceling all the common denominations, and I wind up with what? Centimeters as the label. So I now do the resulting arithmetic, and I get what? 1 foot. Well, I wrote it clearer down here. Maybe you can see it better. See, 1 times 12 times 2.54. That's 12 times 2.54. Remember, you can use the calculator now, but there are worse things than having to multiply by 12 without the calculator. The numerator becomes 30.48, and remember the label is centimeters. The denominator is 1, and when the denominator is 1, we can omit it. So the answer is there are 30.48 centimeters in a foot. Now, every so often, you'll see a bumper sticker that says think metric, which is interesting because most people can't even think English. Basically, if your main aim is to convert from metric measurements to English or vice versa, there are easy ways to do this without having to memorize. You see, we can do that any time that we want. As I say, I want to avoid getting into any kind of political discussions over the metric system. Let me simply say this. I don't know the lira system. I don't know the shekel system. I don't know the ruble system. I don't know the franc system or the mark system. But I can shop around in America. And the only time I'm going to have to know what these other systems are is if I become an international financier or if I become a tourist, in which cases I'll learn those things. And I feel the same way personally about the metric system. If I need an answer in the metric system and I can think English, I can always translate into metric as my second language. And let me just give you a for instance over here. Let's suppose we take the fact that we now know that there are 30.48 centimeters per foot. And if we forget that, we can always derive that by remembering that there are 2.54 centimeters per inch. And if we forget that there are 2.54 centimeters per inch, we can look it up. If I were to ask you right now, what is the population of Denver? There's a good chance you don't know. And if you do know, I'd be a little bit suspicious as to why you would know that, but that's not the important point. If you really wanted to know, you can look it up. And if you really want to know how many centimeters there are in an inch, you can look it up if push comes to shove. But let's suppose, for the sake of the next part of the discussion, that you know that there are 30.48 centimeters per foot. So I say to you, which is longer, 500 centimeters or 17 feet? It's a very simple comparison problem. You can either take the 500 centimeters and convert that to feet, or you could have started with the 17 feet and converted that to centimeters. Let's start with the centimeters and convert that to feet. Say I have 500 centimeters, I want to see how many feet that is. So to get rid of the centimeters in the numerator, I put it in the denominator. And since I know the relationship between centimeters and feet, and by the way, if I didn't know that, I would just redo the previous problem. I would go from centimeters to inches, then from inches to feet. But I know that there are what? 30.48 centimeters in 1 foot. So what do I do now? The denominations come out correctly. I multiply the two numerators together to give me 500. I multiply the two denominators together to give me 30.48. I take my calculator, I divide 500 by 30.48, and I get 16.4 feet, rounded off somewhat. But the important thing is what? 500 centimeters is only 16.4 feet, so 17 feet being longer than 16.4 feet must be more than 500 centimeters, okay? And if I had started with the feet, I could say, okay, to go from feet to centimeters, I'll put feet in the denominator, see that will cancel them out, centimeters in the numerator, that puts 30.48 in the numerator. You see, notice what happened. In this problem, the 30.48 went into the denominator because centimeters was in the denominator. In this problem, it went into the numerator because centimeters was in the numerator. At any rate, I now do the required arithmetic. 17 times 30.48 is 518.16 centimeters. So 17 feet is longer than 500 centimeters. Either way, I get the right answer. And I don't have to understand what a centimeter looks like to be able to get the problem this way. However, if I did understand centimeters, obviously intuition combined with logic is better than logic alone. Okay? When people say, I'd rather be poor but healthy than rich and sick, that's very nice, but it's a cop-out. Don't settle for that. Say, I'd rather be rich and healthy than poor and sick. And if I can't have both of them, then I'll settle for whatever I can get. But basically, notice how this dimensional analysis allows you to apply constant rates to any kind of measurement. And here are some common English rates that we'll be using throughout the course. There are 12 inches per foot, 3 feet per yard, 1,760 yards per mile, which some of you may have learned as 5,280 yards per mile. Those of you who run track may remember racing events called the 440 and the 880. Notice that 440 is 1/4 of 1,760. The 440 refers to 440 yards, which is 1/4 of a mile. The 880 is 880 yards, which is 1/2 a mile. At any rate, 16 ounces when we deal with weights are a pound, and 2,000 pounds make 1 ton. Okay? Now, the English measurements that we use, this is very important. The English measurements were invented and discovered at a time before place value. So people wanted numbers for conversion factors that were easily divisible without leaving remainders. See numbers like 12, 60, 360, etc. And that made a problem when the decimal world came in, when place value came in. Let me give you an example. See, English measurements weren't meant for decimal fractions. I say to you, to the nearest inch, how long is 0.56 feet? See, and what does that mean? 56 hundredths of a foot. And people love to say a half a foot. Somehow this confuses them, and what they forget is what? That there are 12 inches to a foot. You see, basically, if you're going to do this problem the way I just suggested, you want to convert from feet to inches, so starting with 0.056 feet. Feet's in the numerator, you put feet in the denominator, inches in the numerator, 12 inches equals 1 foot. You cancel the denominations. The denominators are 1, so we forget about that. The numerator is what? 0.56 times 12. That comes out to be 6.72. And so, in other words, to the nearest inch, 0.56 feet is 7 inches. And somehow 0.56 doesn't suggest 7. On the other hand, watch what happens when we deal with money, which is based on a decimal system, a trade-in value of 10. See, but anyway, let me just show you another way of looking at this first. If you don't like the dimensional analysis part, just read this linguistically. 0.56 feet means 56 hundredths of a foot. That's 56 hundredths of 1 foot. A synonym for 1 foot is 12 inches. Of means times, so you're going to multiply 0.56 times 12 and label the answer inches, and you get the same 6.72. But now suppose I say to you, to the nearest cent, how much is $0.56? See, and watch what happens now. See, I say, okay, I have $0.56. I want to convert that to cents. That means I have to get rid of the dollars and bring in the cents. So I divide by dollars. In other words, dollars was in the numerator. I put it in the denominator. Now I put cents in the numerator. I now do the resulting arithmetic. The dollars cancel. 0.56 times 100. In the decimal system, to multiply by 100, you just move the decimal point 2 places to the right. The numerator becomes 56. The denominator is 1, so I forget about that. So $0.56 is 56 cents. And do you notice that when we see something written like this, how should we read this technically? 56 hundredths of a dollar, but since a hundredth of a dollar is a cent, we look at this and read it this way very often, don't we? That's the beauty of trading in a decimal system. But there's a flip side to this story. See, there's a rebuttal. Turnabout is fair play. Decimal measurements sometimes weren't meant for common fractions. In other words, when you take a decimal measurement like a dollar, suppose I say to you, how many cents are there in 1/3 of a dollar? See, 1/3 of 100 is 33 and 1/3. That's a mixed number. But you see, if a dollar was made up of a multiple of 3 cents, then 1/3 of a dollar would be no problem at all. So you see, the question of 10 versus 12 continues to come up. Now, what happened is, historically, the advocates of the metric system came about after the invention of place value. See, it's not the meter which is important. I mean, it's not really important whether a meter is this long or this long. What is important is that in the metric system, 10 of any one denomination is worth 10 of the next higher denomination. And that means 2 things. First of all, you don't have to memorize, like, let's see, 12 inches to a foot, but 16 ounces to a pound, and 24 hours to a day, and 60 minutes to an hour. You see, it works that way, first of all. And secondly, because all of the denominations and the trade-in values are powers of 10, the conversions are made just by moving a decimal point. Okay? So here's the way the metric system came about. They picked a length that was called a meter. And now all they did was, and this is simple, people make a big issue over this, but it's really simple. What they did was, they took the regular place value that we've already discovered. They took the regular place value and used the adjectives here to modify meters. Isn't it, if I don't put the word meter in here, don't you see that this is a regular place value system? See, ones, tens, hundreds, thousands this way, tenths, hundredths, thousands this way. But now remember, numbers are adjectives modifying nouns. In the metric system, we just call it what? 1 meters, 10 meters, 100 meters, 1,000 meters. A tenth of a meter, a hundredth of a meter, a thousandth of a meter. And we gave these things names. For example, 1,000 meters was called a kilometer, kilometer we pronounce it, but kilo is the Greek prefix for 1,000. Kilo means 1,000. In fact, in street talk, when people talk about drugs and they talk about a kilo, they're talking about a kilogram. A gram is a metric measurement that we'll talk about in a few minutes. It's a metric weight. And a kilogram simply means 1,000 grams. And if I wanted to apply that to dollars, I think the slang expression for $1,000 is a grand. We could have called it a kilo buck or a kilo dollar. You see the idea? In fact, the words dime and decimal almost beg this interpretation. In fact, let me just show you some more over here. You see, 100th of a meter was called a centimeter, and centi means 1/100th. Now, what's a penny called in our system? It's a cent, isn't it? Think of a cent as being an abbreviation for a centi dollar. See, the word dime is a corruption of the word decimal. We could think of a dime as being a decidollar, see, a tenth of a dollar. And there is a measurement called a decimeter, but I'm only emphasizing in the lecture the ones that are used the most frequently. The other measurements are given in the textbook, but for the time being, the words that we will use is 100th of a meter is called a centimeter, just like 100th of a dollar is called a cent, which could be viewed as an abbreviation for a centidollar, and 1,000th of a meter, from the Roman numeral m, millim, is called a millimeter. Just like there was once a coin that was 1/10 of a cent called a mill, that could have been called a millibuck, a millidollar. But the important point is, watch how this system works. You see, 10 millimeters makes 1 centimeter. 100 centimeters makes 1 meter, just like 100 cents makes $1. And 1,000 meters makes 1 kilometer. See, kilo means 1,000. At which point you may say to me things like, how am I supposed to memorize all that? Hey, you memorized how to spell words in English, and if you remember our lecture in Module 1, if you can do that, this should be a piece of cake for you. There aren't that many things to memorize, and after you think about the prefixes a few times, you get them fixed in your own mind. But watch how easy the arithmetic works this way. Suppose I say to you, how many centimeters are there in 2.63 meters? See, 2.63 meters means 2.63 of a meter. Of still means times. A meter is still 100 centimeters, and to multiply 2.63 times 100, you just move the decimal point 2 places to the right. In other words, to say how many centimeters are there in 2.63 meters is the same problem as saying how many cents are there in $2.63. It's 263 cents. And by the way, if you don't like to think it through this way, go back to our dimensional analysis. You take the 2.63 meters, you want to get rid of meters and bring in centimeters. What's the relationship between meters and centimeters? That's never going to change. It's 100 centimeters equals 1 meter. Now you do the arithmetic, and that tells you to do what? Move the decimal point 2 places to the right, and you get the same 263. And if you're going from a smaller denomination to a bigger denomination, you're just going to divide. See, people get confused about that. You see, because a foot is bigger than an inch, in a given measurement, there's going to be fewer feet than there are inches. People always like to get those mixed up. See, because the foot is bigger, it's not going to take as many. See, in a 24-inch length, there are going to be 2 feet. So people sometimes get mixed up. And if you can overcome that, that's fine. But if you can't overcome it, watch how we handle it. It says, how many meters are there in 200 millimeters? So the way we handle that is, we're given 200 millimeters, we want to convert that into meters. How do we do that? We want to get rid of the millimeters, so we put them in the denominator, so they'll cancel. We want to bring in meters, so we put that in the numerator. What's the relationship between millimeters and meters? That's not going to change. It's still what? 1,000 millimeters per 1 meter. Now you can say what? 200 times 1 is 200. The denominator is 1,000. To divide by 1,000, you move the decimal point 3 places to the left. That gives me 0.200 meters. I really don't need this. Those zeros don't mean that much. So basically, how did you convert millimeters to meters? Instead of multiplying by 1,000, you divided by 1,000. And the logic behind that, if you don't want to use the dimensional analysis, is that you went from the smaller unit to the bigger unit, so you're going to need less. Okay? Now, here's the point. If a person has been brought up in the English system and has never heard of the metric system, they're fine. They can get along fine. And if people were born into the metric system and never heard of the English system, they can get along fine. Just like the person who knows only English, as long as he stays in America, is fine. And the person who knows only Spanish, as long as they stay in a Spanish-speaking country, they're fine. It's only when the two cultures come together that you have to be able to translate from one language into another. I'm not saying it's not nice to be able to translate from one to the other, but by necessity, it's only when two diverse cultures mingle that each has to learn to appreciate the other. I guess we call that détente or coexistence. Well, see, the same thing happens now. You can live entirely within the metric system, and you can live entirely within the English system. But if you have to work outside of your regular area of expertise, whichever one you're comfortable with, the other one has to be your second language. And all you have to do, once you've memorized how each system reacts in its own right, is to find one crossover, one bridge, one way of getting from one to the other. So here's one way we could do it. Take a particular length. If I have a certain length, this length is this long, whether I measure it in inches or feet or kilometers or what have you. The length doesn't change, only the adjective that modifies the noun that's measuring that length changes. In other words, if something is 24 inches long, it's also 2 feet long. The length hasn't changed, just the adjective changed. So what we could do is, and I'm just making this up, take a piece of string that you've measured to be 100 inches, 100 inches long. Now you say to the person who works in the metric system, you say, "Sir, would you measure this piece of string?" Well, he measures it, and he gets 254 centimeters. Well, why did he get 254 centimeters? Well, that's what it said on this ruler. It just came out that way. Had to be something. So what does this say? This piece of string is the same length whether I'm using centimeters or inches, so that says there are what? 254 centimeters per 100 inches, doesn't it? See the rate here? There's a rate of what? 254 centimeters per 100 inches. And now, to convert that to 1 inch, all I have to do is what? Divide by 100. That means move the decimal point 2 places to the left. If I move it 2 places to the left here, I also have to move it 2 places to the left here. So I get the relationship that there are 2.54 centimeters per inch. And once I know that relationship, once I know this relationship, I can now cross over from the metric to the English at will. Oh, by the way, I could also have elected to divide both sides of this relationship by 2.54 instead of by 100, in which case I would have found out what? Instead of centimeters per inch, I would have found out inches per centimeter. But these are things you can practice on as you're going through the text and the study guide. But let me show you now how you can convert some of these things. I say to you, how many yards are there in 100 meters? How many yards are there in 100 meters? Now this is tricky. You have to get from meters, which is a metric measurement, to yards, which is an English measurement. So somehow you have to reduce the metric measurement to the crossover thing. Remember, the only way I'm asking you to memorize how you get from the metric to the English is 2.54 centimeters per inch. So I have to get from meters to centimeters, then from centimeters to inches, then from inches I'll go to yards. And watch how this works one step at a time. See, I've got the 100 meters. I want to get rid of the meters, but meters are expressible in terms of centimeters, namely what? There are 100 centimeters per 1 meter. So gets rid of the meters for me. Now I want to get rid of the centimeters. Centimeters are in the numerator, so I put them in the denominator. What's the relationship between centimeters and inches? There are 2.54 centimeters in 1 inch, so I put the 2.54 next to the centimeters. Now I've got what? The centimeters are gone, so my label is inches so far. Remember, I want yards. Inches are in the numerator. I know the relationship between inches and feet, namely what? 12 inches per 1 foot, so I put the 12 next to the inches. Do you start to see it? This is the same stuff over and over and over again. Now I've got the answer in feet, but I don't want feet. I want yards, so I divide by feet, multiply by yards. There are 3 feet to 1 yard. Now my rough check is, when I'm all done, only the label I want should be present. Now I do the resulting arithmetic. It's 100 times 100 divided by 2.54 divided by 12 divided by 3. And hopefully you see the advantage of using a calculator now. And we wind up with 109.36 yards per 100 meters, or if you wish, you could say what? 1.0936 yards per meter. And if you want meters per yard, just flip this thing over, right? 1 meter over 1.0936 yards. There's an interesting story behind this. It's not that critical, but I thought you might be interested in knowing that. When the Americans trained for the Olympics, the first time that the Europeans ran the Olympics in metric distances, the Americans trained in the 100-yard dash. When they went over to Europe to run in the Olympics, they ran the 100 meters. And what happened was the Americans tired very badly over the last 10 meters. And the reason was that the Americans were used to running 100 yards. They get tired when the 100 yards were used up, but they had to run how much? Almost an extra 10 yards to run the 100 meters. In other words, basically, 110 yards is a 16th of a mile. So this is almost a 16th of a mile. In other words, 100 meters is about a 16th of a mile. And we sometimes in races refer to a 1,600-meter run as the metric mile. Just again, a little bit of folklore to show you how these things come up. Now, sometimes people word the problem in reverse. They'll say, how many meters are there in 100 yards? You see, if you're nervous about the metric system and the English system, and people talk to you about meters per yard and yards per meter, it's very easy to get mixed up as to whether you should multiply or whether you should divide. But for example, since we have just found out that there are 1.0936 yards per 1 meter, the 1.0936 is going to modify yards wherever it appears. So in other words, when somebody says, how many meters are there in 100 yards? I say 100 yards equals blank meters. I want to get rid of the yards, so I put it in the denominator. I want to bring in meters, so I put meters in the numerator. What's the relationship? The 1.0936 goes next to the yards. The 1 goes next to the meters. And even if I don't understand what I'm doing, it's what? 100 in the numerator, 1.0936 in the denominator. I just do what? See, the labels check out. So I just do the required division. 100 divided by 1.0936, that tells me there are what? 91.44 meters per 100 yards. And if I hadn't done problem 13 first, I'm not going to go through this, but I just want to show you. If I want to convert from yards to meters, what do? I go from yards to feet and from feet to inches. And why do I go to inches? That's my crossover. Because from inches I can go to centimeters, and from centimeters I can go to meters. And in fact, if I put these numbers in, see 3 feet is 1 yard, 12 inches is 1 foot, 2.54 centimeters is 1 inch, and 100 centimeters to a meter, I can actually take 3 times 12 times 2.54, divide that by 100, and that number will be the conversion factor from yards to meters, and I'll never have to do anything else again that way. But why memorize all these things when you can always get from one to the other by simple logic? Let's switch now to handling weights. In the English system, they picked something called a pound. That was also not just a weight, it was also a money thing. I once went to England to go on a diet because I had heard about a guy who lost 32 pounds in one night in England. I didn't know it was playing poker. I thought he was losing weight, but that's a different story. At any rate, we divided the pound into 16 equal parts. Each was called an ounce, so 16 ounces is a pound. 2,000 pounds is called a ton. And how do we learn those things? We memorize them. Now, in the metric system, what they did is they took a little cube, see 1 centimeter by 1 centimeter by 1 centimeter. That's called the 1 centimeter cube, and that's called a cubic centimeter. They filled that with water, and that weight was called 1 gram. Then using the usual decimal system, 1,000th of a gram was called a milligram. In other words, just like 1,000 millimeters make a meter, 1,000 milligrams make a gram. And just like 1,000 meters make a kilometer, 1,000 grams make 1 kilogram. And they went one step further, and this came in later. 1,000 kilograms was called a metric ton. And I'll show you in a little while why that happened. Why was 1,000 kilograms called a metric ton? And the answer was that it came out very close to being an English ton. And we'll just go through that in a few minutes. The key, again, all you have to do is have a crossover. A crossover. In other words, to go from the metric to the English, someplace I have to have a cultural exchange. And it turns out that the relative sizes over here is that the same weight that requires 1 pound in the English system takes 454 grams to make that measurement. So suppose I were to say to you, how many pounds are there in 1 kilogram? See, 1 kilogram equals blank pounds. The trick is the crossover is in terms of grams per pound, not kilograms per pound. So from kilograms, I have to go to grams, and then from grams, I go to pounds. And you see what happens over here, there are what? 1,000 grams per kilogram, so I put the 1,000 next to the grams, okay? Then there are what? 454 grams per 1 pound, so the 454 modifies the grams. How do I do this problem now? I first check to see that my labels are right. Pounds is left, that's okay. 1 times 1,000 is 1,000. 1 times 454 is 454. So the answer is going to be 1,000 divided by 454, taking out my trusty calculator. And in seconds, this is the answer I get. Look at all them decimal places. 2.202643172, which rounded off the way this thing looks, is roughly there are 2.2 pounds per kilogram. And the reason I bring this up is a metric ton is 1,000 kilograms. So if I multiply both sides of this rate by 1,000, that shouldn't change anything. The rate should stay the same. So multiplying both sides by 1,000, that means what? Move the decimal point 3 places. This says 2,200 pounds. 2,200 pounds is a metric ton. And in fact, in some American books, they call 2,000 pounds a short ton and 2,200 pounds a long ton. And the reason they do that is that what we call a long ton turns out to be the metric ton. In other words, 1,000 kilograms is roughly 200 pounds heavier than the 2,000 pound English ton. By the way, again, if all this stuff bothers you, but you're not afraid to count by multiples, look, if there are 454 grams in 1 pound, there's going to be twice that many grams in 2 pounds, and so 2 pounds is 908 grams, which is a little bit less than 1,000 grams, and now if you switch to long division, divide the 454 into the 1,000, you get 2 with a remainder of 92. That's 92 of the 454 grams you need for another pound. So without any decimals and without any calculator, you could say what? The exact number of pounds per kilogram is 2 and 46 over 227, and I think you can begin to sense that the 2.2 seems a nicer way of handling that. Another thing that's interesting in terms of adjective versus noun. We talk about a dose of medicine being 5 milligrams or 10 milligrams or 20 milligrams. I want to show you why it's so important in certain areas to really be able to measure. See, we don't think of an ounce as being very big. Let's tackle the problem of how many milligrams there are in 1 ounce. See, from ounces we can convert to pounds, from pounds to grams, and from grams to milligrams. I'm speeding up the tempo of the conversions because you should be getting more familiar with them as we go along. See, there's what? 16 ounces to 1 pound, 454 grams to 1 pound, and there's 1,000 milligrams to 1 gram. So let's check the labels again. Ounces cancel, pounds cancel, grams cancel. We're left with milligrams. The numerator is 454 times 1,000. The denominator is 16. 454 times 1,000 divided by 16 is 28,375 milligrams in just 1 ounce. Can you imagine how small a milligram is? How if you double the number of milligrams from, say, 25 to 50, you can kill a patient, and yet it's what? Almost a minuscule part of an ounce. And again, you could have done this problem another way. If there are 454 grams per 1 pound, that's the same as saying 450 grams per 16 ounces. Therefore, you divide 16 into 454, and you get grams per ounce. In other words, there are what? 28.375 grams per ounce. Move the decimal point 3 places to the right, and you have the same 28,375 milligrams per ounce. Another place where we use English and metric system, it really comes up in the next module, but I'll give you a prelude to that now, and that's called areas, the amount of space inside a region. See, look, for example, at this square. It's 3 inches on each side. I can therefore draw 3 1-inch vertical strips, 3 1-inch horizontal strips, and you'll notice that that gives me what? A total of 9 1-inch squares. See, I've counted that for you. And in fact, if you multiply these two numbers together, the 3 times 3 gives you 9, and inches times inches gives you square inches. In other words, there are 9 square inches in a 3-inch square, and we measure area in square units. Now, the basic metric area measurement is called a hectare, and that's a square that's 100 meters by 100 meters. And that's what? 100 times 100 is 10,000. That's 10,000 square meters. I'm just telling you this. You don't have to know any of this to do the problem, you see. The English system, and I never knew where this came from, I still don't, but we can look it up. An acre is what you get when you take a square mile and divide it into 640 equal parts. In other words, to use this without fractions, there are 640 acres in 1 square mile. So basically, we have what? A metric system that deals with hectares, an English system that deals with acres. If I'm buying land in a country that uses the metric system and I'm used to the English system, I'm thinking acres, they're talking hectares, I have to have a second language. And it turns out that the number of acres that fit into a hectare, and I'll do this as a supplement to Module 11 later, is 2.471 acres per hectare. And you can memorize that. In fact, for the exercises in this assignment, for the self-test, you are free to memorize that there are 2.471 acres per hectare, that there are 2.54 centimeters per inch, and 454 grams per pound. And if you don't remember them, just look them up if you need them when you're doing the problems. I don't see any sense in making you learn them, because if you use them enough, you're going to remember them anyway. And if you don't use them enough, the important thing is to know how to use them once you look them up. But let me just conclude with a couple of more examples. Suppose I wanted to convert hectares to acres. How many acres are there in 20 hectares? Remember, there are 2.471 acres in 1 hectare. By the way, which is the bigger one, the acre or the hectare? Be careful. The bigger adjective is modifying the acre, so the hectare must be bigger. See, it takes more than 1 acre to make up 1 hectare. But can you notice how your mind can freeze if you're afraid of the concept? You can get these things reversed. See, basically the way I would solve this problem is I say, look, if there are 2.471 acres in 1 hectare, in 20 hectares, there should be 20 times as much. So the answer is just 49.42 acres per 20 hectares. But if I didn't know that, and I was afraid, I could say, look, they're giving me the 20 hectares, I want the answer in acres. So I'll cancel the hectares, bring in the acres, simply go back to the memorized relationship. The 2.471 modifies the acres, the 1 modifies the hectares. What happens? The hectares cancel, and I still wind up with doing what? Multiplying 2.471 by 20, which is the same thing I did when I knew what I was doing. See, the beauty of dimensional analysis is that if you're good at it, it makes you even smarter. But if you're not good at the concept, but you know dimensional analysis, you will correctly solve problems that you might have no feeling for. And that's a heck of a lot better than not solving the problem at all. Now see, what if the problem was reversed? See how similar 17 and 18 sound? 17 said how many acres are there in 20 hectares. 18 says how many hectares are there in 20 acres. And the point is, I don't have to worry about that. I say, look, I'm given the 20 acres. I want to convert that to hectares. So what do? Acres are in the numerator. I put them in the denominator. I put hectares in the numerator. How do the adjectives go? The 2.471 modifies the acres. The 1 modifies the hectares. So now what happens? I check to make sure I've got the right label. This is what? 20 divided by 2.471. That comes out to be 8.093889114 hectares per 20 acres. And I did it on my calculator. That's how fast this happens. And so basically, rounded off, say, to the nearest hectare, there are 8 hectares in 20 acres. And again, how could you have done this problem? You could still have written down that there are 2.471 acres per 1 hectare. Since you want to know what 1 acre is, you divide by 2.471. And now when you want to know how much 20 acres is, if 1 acre is this much, 20 will be 20 times that much. And that would be 20 divided by 2.471, which is exactly what you had over here. And as a last word, don't be afraid to estimate. If 2.471 scares you, notice that that's very close to 2.5 or 5/2. So when you were taking 20 acres and multiplying that by 2.471, roughly speaking, that should have been the same answer as if you were multiplying by 5/2. that would give you 50 right away, and that comes very close to matching the 49.2 or whatever it was that we got the other way. Similarly, when you took the 20 acres and wanted to divide that by 2.471, replace 2.471 by 5 halves. Dividing by 5 halves is the same as multiplying by 2/5. And 4 times 2 is 8, which checks very closely with our 8.09. And what I'm hoping that you saw in today's lesson is something that will help you stop being faked out. Remember I told you in our preface lecture that many people miss out on mathematics because of psychology rather than lack of mathematical ability. Please learn this dimensional analysis technique. And notice that as long as you're given the ratios, you can always find the answer by this method, even if you don't understand what's going on. And you can use that time to buy additional time to learn to understand what is going on. Then you'll have the best of both worlds. At any rate, that concludes our lesson for today. I hope you'll work diligently on the rest of Module 10. Until that time, work hard, have fun, and stay young.